Okay, so welcome back. So this video is going to start chapter 20 for us. We're going to start talking here about something called chemical thermodynamics. And to give you an overview of what this chapter is about, we're really going to start to understand why chemical reactions occur and be able to predict whether or not a given reaction is going to be spontaneous or not spontaneous. And that's actually going to be kind of big words for us in this chapter, this business of spontaneous or non-spontaneous. And we're going to use enthalpy to help us do that, but we're also going to use something new, and that's what we're going to learn about first here in this video, something called entropy. And entropy in a chemical system is given the symbol capital S, okay? So this capital S, we're going to see that a lot here later in the video. And that entropy is going to be something that we're going to want to learn about, okay? So now entropy is oftentimes described as the disorder of a chemical system. It's sort of randomness, if you want to think about it that way. But what it really boils down to physically is the number of different ways that a chemical system can distribute its energy. Nature really prefers having a large number of possible avenues or routes in which it can distribute its energy. And anything that increases the ability of a system to distribute its energy will increase its entropy. And that tends to be good for chemical reactions. And we'll see that as we proceed through chapter 20, okay? So what are we going to do in this video? What are some things that we're going to want to learn? We're going to introduce ourselves to this idea of entropy. We're already starting to do that right now. We're going to want to try to wrap our minds around this concept of entropy and something called microstates, which we're going to get to here in a few minutes. We'll want to be able to qualitatively predict what type of chemicals, what type of materials have a high entropy, and what types will have a low entropy. And then we're going to want to know something about how does entropy change with temperature and different phase transitions. Like if ice melts, does that increase the entropy or decrease the entropy? And we'll talk about that here later. We want to be able to qualitatively predict entropy changes for different reactions or these phase changes. And then we're going to, at the end of this video, I forgot to fill it in, but we're actually going to compute what I'm going to call delta S. Delta S, triangle S, okay? And that's going to be the entropy change for a reaction. I'm going to teach you how to do that later in this video, okay? So that is where we are headed. So let's start in that direction, okay? So the first thing that I want you to learn about here is microstates and macrostates, okay? Microstates and macrostates. So it turns out that entropy has something to do with this first one. These so-called, microstates, okay? So what I'd like to do is consider flipping a coin 2 times. We're going to flip a coin twice, okay? Think of all the possible outcomes. Now, going into this, if we're going to flip this penny twice, we might just think that we're pretty likely to get 1 heads and 1 tails out of our 2 flips. This seems most probable, but can we explain why that is, okay? So let's think about what can possibly occur, all the possible outcomes for our first flip and then our second flip, the sequence. So one possible outcome is that we get the heads and then we get the tails on the second flip. So 1 heads, 1 tails. Another outcome is that we get our tails flip and then our heads. So again, 1 heads, 1 tails, just backwards order, right? Now a third option is that I get heads and heads. And then the last possible outcome is that I get tails and tails. So each one of these cases that I'm describing to you here are a possible microstate. It's a microstate. It's the exact sequence or order of the outcome. And there's 4 different possibilities for this 2 sequence flip or two flip sequence of our penny, okay? Now, earlier when we went into this, we said the most probable outcome is that I get one heads and one tails. Well, why is that? It might seem most probable, but why is that? Well, the reason why it's most probable is because two of our microstates lead to that outcome, right? Two of them lead to that outcome. 50% probable that we get one heads and one tails because two of our four microstates leads to that outcome. However, going into this, it turns out that any of our four outcomes is equally probable. In other words, getting outcome one has the same probability as outcome four. Okay, so going into this, any four of these microstates are equally probable. It's just that the macro state that we call one heads and one tails has two microstates associated with it, and these other microstates, whether it's all heads or all tails, only have one microstate associated with it. So this one's 25% possible, this one's 25% possible, and these two together are 50% possible. Okay? So this is, I guess, the difference between the microstate and the macrostate. I'm not too concerned about the probability of the coin flipping at this point. But what I'd like to get you to notice is the difference between the microstate and the macrostate. They're not the same, right? The microstate is the individual sequence of flips, and the macrostate is this outcome or the result. You know, one heads, one tails, or two heads, two tails, okay? So the one heads, one tails macrostate is most likely only because two of the microstates lead to that identical result, okay? So that's kind of what I'm getting at with this discussion here. Now that we introduced ourselves to microstates and macrostates, what I'd like to do for a second is to continue this experiment, continue this coin flipping thing. Now what I'm going to do is instead of flipping it 2 times, I'm going to flip it 4 times. Okay? So 1, 2, 3, 4. 1, 2, 3, 4 is shown, of course, 4 flips is shown over here on the right of this slide. Now, what this table shows is all possible outcomes for our 4 flips. I could get 4 heads and 0 tails. Maybe I get 4 tails and 0 heads. I might have 3 heads and 1 tails. That's shown here in blue, through here. And the only difference between these 4 microstates is the order which the heads appears, okay? Alternatively, down here in red, I might get 3 tails and 1 heads. And again, what's different between these 4 microstates is just the order with which we get the heads or the tails. And then right here in the middle, I have this green area, or I get 2 heads and 2 tails, okay? So there are 16 possible microstates or orderings that the flips could occur in terms of their heads, tails behavior. But 2 of them lead to the case where I only get 4 heads or 4 tails. 4 of them give me 3 heads and 1 tails. 4 of the possible microstates also give me 3 tails and 1 heads. And 5 of them, and through here in green, give me the most possible outcome, where I get 2 heads and 2 tails. So again, we can start to consider the probability with which any of these outcomes in terms of the macrostates occur by how many microstates represent each macrostate or each grouping, okay? So the most probable macrostate is the ones in green, because 5/16 chance of obtaining one of those. So we could then plot the probability of encountering any one microstate as a function of the total number of heads coin flips. And we see the most probable is getting 2 heads. And getting all 4 heads is not very probable, and likewise, getting 0 heads is not super probable, only about a little over a 5% chance of getting either one of those. But there's about 37.5% chance of getting this green two heads and two tails situation, okay? So we can see that the distribution of probability kind of spreads itself out, doesn't it? Okay? All right, now we've been talking about pennies, flipping pennies, right? And we all know this is a chemistry class, so we might want to actually talk about some science or chemistry here rather than just probability or penny flipping. So it turns out that this idea of macrostates and microstates certainly extends to chemical systems too. And the guy who kind of came up with this idea was an Austrian physicist named Ludwig Boltzmann back in the 1800s. And he started to think about chemistry as it relates to these microstates and macrostates, and specifically this business of entropy. So to start off this conversation and transition to a chemical example, let's think about an experiment in which we take 4 different atoms. Now these atoms are different colors. So look carefully at these flasks, because we're going to place the atoms inside these flasks. And the flasks are connected. You can see it over here by a small tube, okay? And there's a bulb down here and there's a bulb down here. Now these are glass flasks. There's just 2 ends, they're equal volumes. And we connect them both through a small tube. And inside each flask, I'm going to place 4 atoms. Now these atoms are colored, just so we can keep track of them. There's one that's blue, one that's red, purple one, and a yellow one, as we can see easily down here in the bottom right. Now, how can these atoms distribute themselves? These are gas phase atoms, so they're free to move about, right? So how can these gas phase atoms distribute themselves inside of these flasks? Well, there's many different ways. Many different ways, okay? We could have the situation that we see here on the far right. This is possible, labeled number 5. All 4 atoms might be in the right flask at any given instant in time. Alternatively, we could have the opposite case. All 4 atoms could exist in the left-hand flask at any given instant in time. Now, if you think about whether this is very probable or not, I don't know. I don't really think it is, right? I mean, we probably wouldn't guess it's that probable that all 4 atoms end up in one flask or the other. Probably we have some atoms in the right flask and some atoms in the left. You think that this one here in the middle is probably most probable. And if we look at why that is, well, all these states here in the middle, all the individual microstates in the middle, whether it be this first one, the second one, so on and so forth, all these individual microstates have 2 atoms in the left flask and 2 in the right. So, while which atoms are in each flask differs, right? You can see here it's the red and the yellow in the right. And then over here it's the purple and the blue in the left. And then down here you've got the opposite situation and so on down the line, right? You can see different atoms in each flask, but each of these individual microstates leads to a macrostate in which there's 2 and 2 in each flask, right? And likewise, in this case here, macrostate 4, you've got 3 and 1. In macrostate 2, you've got the opposite case, 3 in the left and 1 in the right. So we've got 16 possible microstates, right, if you add up all the flasks. But again, the most probable is the macrostate 3. 1, 2, 3, 4, 5, 6 are present right there, okay? So the most probable outcome is where we have 2 and 2, because that's where we have the most macrostates. And the least likely is macrostate 5 or 1, which are equally likely, because there we've got all 4 in one container. And only one of our microstates leads to that particular macrostate outcome. So indeed, we can see how, or at least begin to see how, this idea of microstates and macrostates can extend to chemistry, okay? Now, in reality, we have to talk about a lot more than just distributing atoms in different flasks, okay? That's kind of a usual visual aid, right? To think about these microstates. But in reality, entropy is going to really boil down to something very different. Entropy is going to boil down to the dispersal or distribution of a system's energy, and not really just distributing atoms amongst flasks, okay? So what do I mean by that? Well, every molecule in a sample has some internal energy associated with it. Every molecule can vibrate, rotate, and translate. And this is how energy really manifests itself in molecules in chemistry, okay? Now, what do we mean by these words? Vibrate, rotate, and translate. Let's start with translate, okay? Translational motion is the energy of movement. It's basically taking this molecule, which appears to be carbon dioxide, and moving it through space, translating it through space. It moves left, right, up, or down, okay? That's translation. When a chemist says translational energy, that's what we mean. It's translational motion, translational energy. It's basically a kinetic energy, right? But there are other ways that energy can be stored in a chemical system. There's rotational motion. In rotational motion or rotational energy, our molecule of interest will spin or rotate. It just spins around, kind of like a top, okay? And energy can be stored in the rotation of molecules. Energy can also be stored in vibrations. In a molecule such as this one, which is CO2, of course we know that chemical potential energy is stored in the bond. Now, these bonds here and here are not stagnant. They can actually flex or stretch. So for instance, we could have what's called symmetrical stretching, where the carbon atom in the middle of the bond and the oxygens will flex or stretch in the left or right direction compared to one another. A symmetrical stretch yields both bonds increasing in length ever so slightly. Now, they will restore and come back again unless the bond just breaks to the equilibrium bond position. But bonds are constantly stretching. This is constantly going on. And energy can be stored in that stretching motion. We can have asymmetric stretching. In asymmetric stretching, the only difference is we're still getting stretching or movement of the nuclei with respect to one another, and the bond lengths are changing. But the only difference is that the molecule does not stretch in an equal way. In other words, one bond might get a little longer and the other bond gets a little bit shorter. Okay, that's an asymmetric stretch. We can also have bending motions in our molecules. A bending motion is when the nuclei will sort of flex in the molecule such that the bond angle can change. Okay, now normally at the equilibrium bond position, we'd say that CO2 is a linear molecule. But this bending motion basically moves this carbon nuclei one way or the other, up or down in this particular slide. And that changes the bond angle. Okay, now will it restore towards the equilibrium bond angle? Yes, there will be a restorative force to help that happen. And that's certainly the case, okay? But again, bending is a place where this molecule can store vibrational energy. So in this particular slide, we're considering one CO2 molecule, right? Now remember, a sample of matter is going to contain millions, billions, trillions, and more molecules. And every single one of those molecules can undergo these types of processes, this rotation, this translation, this vibration. And more so, when these molecules bump into one another, say in the gas phase, the molecules can transfer energy back and forth between one another. Now the point to this is that each of these motions, translational motion, rotational motion, vibrational motion, these are all ways that energy can be really stored or distributed within our molecules in our sample. And the molecules are always transferring energy back and forth to one another, okay? And what's important, I guess, about this is sort of what's written down here at the bottom, okay? If we give our molecules the ability to bend, to stretch, to have rotations and translation, we're giving the molecules ways to store or distribute its energy. And that increases the entropy. Anything, on the other hand, which impedes translation, rotation, vibration, reduces entropy. So our molecules like to have lots of options, whether it's translation, rotation, vibration, lots of different ways that it can distribute its energy. And if we impede that, guess what? We reduce our entropy of our system. All right, and that's going to be kind of an important point here in a few minutes. So let's move on with this idea then, okay? Let's just think of kind of like almost like a cartoonish type experiment. We're going to consider a sample of matter and its internal energy. And we're going to basically isolate a couple of atoms inside this box. Okay, it's an imaginary box. And inside this box, I'm going to place two atoms. The blue one and this orange colored one, okay? Just two atoms inside the box. We're going to consider those. However, the atoms within this box contain some internal energy. Now, how can I think about storing this energy or manifest this energy within this box? Well, there's a large number of possible ways. Now, to sort of simplify this, instead of talking about the specifics of vibrations or translation or rotations, what I'd like us to do is just think about these two molecules within the box and assigning imaginary energy units to them, we're going to call quanta, okay? Sounds very scientific, right? So we're going to assign quanta as imaginary energy or packets of energy to each of the atoms inside this box. Now let's think about how I can distribute the energy between the orange and the blue dot, assuming that my system contains 10 of the quanta and only 10. So my internal energy is 10 quanta, yeah? Now how can I distribute it? Well, if I wanted to, I could give all 10 to the orange, or I can give all 10 to the blue dot, and I can give 0 to the orange. Or maybe I give 9 quanta of energy to the blue dot and only 1 to the orange, and so on down the line until the orange gets all 10 and the blue gets nothing, right? So these are all possible, microstates for distributing my energy, aren't they? They're all possible microstates for distributing my 10 quanta. Now, the internal energy of my system, in all cases, is the same. We're distributing 10 of these energy quanta. It's just that we're doing so differently. Okay? We're doing so differently. So that then leads us to the formal definition of entropy S, the formal definition. So it turns out that back in 1877, a guy by the name of Ludwig Boltzmann, who's an Austrian physicist, came up with an equation to quantify entropy. Entropy S turns out is going to have units of joules per Kelvin, and it can be computed using the equation in this box down at the bottom of the slide. Boltzmann's equation for entropy states that S, the entropy of a system, is equal to K, a number called the Boltzmann's constant, which has the unit and the value of 1.38 times 10 to the minus 23rd. It's joules per Kelvin is the unit. That's in our K right here. We multiply that K times the natural log of W. What is this natural log of W term all about? Well, it turns out that the W is nothing more than the number of microstates that are available in our system for energy dispersal. So if we could possibly count them up, that number of microstates available for energy dispersal is our W. Take the natural log of that, multiply by Boltzmann's constant, and that's the entropy of our system, okay? Now, do you think that we're going to be able to count up the number of microstates in our system? That might be something that sounds difficult, right? So it turns out that we're not going to use this equation a whole lot to compute entropy, but it is the formal definition of entropy. We can also see that what's important for entropy is that entropy scales with the natural logarithm of the number of microstates. The more microstates available, the higher the entropy is of our chemical system. More microstates, higher entropy. That's what this equation basically says to us, okay? So we'll want to reflect upon the ramifications of this, okay? Again, the more ways the system has to distribute its energy, the higher the entropy. That's an important thought. Another thing that I'd kind of like you to begin thinking about entropy is this second one. Our entropy really is an extensive property. The more material that we have, the more ways that we have to distribute the energy within that sample of matter. So the entropy must be higher. So entropy is an extensive property. The more material, the higher the entropy. Entropy is also going to increase with temperature. Higher temperatures give us additional avenues to distribute our energy, which will increase the entropy. Lastly, the effective phase, which we're going to get back to later because that will also be important. Gases have higher entropies than liquids. Liquids have higher entropies than solids. This is because in the solid phase, the particles that make up the solid, whether they be atoms, formula units, or molecules, tend to kind of be sort of locked in place in the solid. They don't have a lot of translational ability. They may be a little impeded, say, rotationally. So because of that, solids will have the lowest entropy of any phase of material. Liquids are kind of in between, and gases, where particles can freely move, will have our highest entropies. So back to that idea. This particular slide shows water in several different forms. It looks like down at the bottom we might have some solid water. This looks like it's ice down here. And we've got some liquid in through here. And then of course this liquid seems to be evaporating up into the gas phase. So it's kind of a very interesting picture. It's got all three phases of water. But if I was to ask you which state has the highest entropy, what will we say? Well, the gas phase up here on the top will certainly have the highest entropy. The reason why that is because in the gas phase, if you're going to think about your mental pictures of our water molecules, well, we've got these dispersed water molecules that are flying around like crazy, aren't they? In whichever direction they're moving, they're translating like crazy, we might say. They're free to rotate at will. And of course, the bonds can always vibrate. So there's lots of different opportunity for dispersal of energy up here, isn't there, in the gas phase? Because of that, it's a very high entropy state. Now, on the other hand, if you think about solid water or ice, if you could look at the individual molecules in ice, you'd see something like this. The individual water molecules are packed in a repeating, very ordered crystalline structure. Look at all that order. These water molecules are in very specific spots down here at the bottom, aren't they? Very, very, very specific spots in a crystalline lattice. This is a highly ordered material. Once that water molecule gets into that individual spot in that crystalline solid of ice that makes up ice, it's not going to translate very much at all. The bonds will still vibrate, and maybe you have a little bit of rotation, perhaps, but that might even be impeded to a certain extent. This ice is a very low entropy state. It's highly ordered material, and there's not nearly as many ways to distribute our energy as there is in the gas phase. Very low entropy. And then here in the middle, we've got a medium entropy state. It's medium entropy, okay? This is liquid water. In our liquid form, the molecules are not nearly as free to translate as they are in the gas phase. The bonds can certainly still vibrate, and rotational movement is also impeded less than ice, but probably more so than the gas. So what we've got is a medium entropy state for the case of our liquid water. You want to be able to predict which states have higher or lower entropies. Another way to think about this then is a plot that looks like this. What this is an xy plot where our y variable is entropy of our sample. And our x variable is our temperature in Kelvin. And what we're going to do here is we're going to go about a phase transition from the solid to the liquid to the gas. And again, this is going to be in water, so H2O, same as the last example. So over here, we've got ice, solid water. Again, it's a crystalline material. The water molecules repeat themselves in this complicated 3D crystalline lattice that's highly ordered. Each water molecule has a very precise spot. So if we start down from 0 Kelvin, which physically can't be achieved, right? But it's hypothetical here, okay? That's absolutely 0. And we start increasing our temperature. We start moving to the right on this axis. We move through the solid phase. Now ice exists all throughout here until we get right here, where we get to the melting point of our solid. Okay, now of course in our case that's going to be here at 273 degrees. Oh, let me erase that. My pen is being difficult to use. But our melting point for water is right here at 0 Celsius or about 273 Kelvin. Now notice what happens all throughout. Doesn't the entropy ever so slightly increase in through here? We get a slight increase. We also see that out here in the liquid phase and will also be reflected in the gas phase, okay? So my point there here is that this slight increase is very common. Entropy always increases with temperature, okay? But where do we see a huge increase in entropy at? Isn't it right there where the solid melts, or over here where the liquid evaporates? That's where we get huge jumps in S, or huge jumps in entropy. So again, rationalizing it. Well, what happens at 273? Well, we get melting of our solid ice into the liquid. We go from a highly structured, ordered material to a liquid sample of water, where now the molecules can flow past one another. Rotational ability is enhanced. Translational ability is enhanced to some extent as well. So the entropy surely increases. Likewise, if we think about a gas, now we've evaporated our liquid into the gas phase, the molecules are free to move and translate. So as a consequence of that, the gas has even higher entropy yet. So we get these huge jumps in the entropy of our material whenever a phase transition occurs. Okay, huge jumps in entropy with phase transitions. Now the next obvious question would be, is there any material that has 0 absolute entropy? Is there any material that has no entropy or no disorder associated with it, or perhaps no microstates to distribute our energy with them? It turns out that there is a reference state for that, okay? Now, we're going to start talking about here something called absolute entropy. And that's the entropy that's reflected in the material, the sample of the material itself. It's an innate entropy of the material, okay? Now, there's several laws of thermodynamics, and we're not going to necessarily present them in order, just because it makes more sense to me to do it in this particular order. But You actually learned about the first law back in Gen Chem 1, so now we're going to switch ahead to the third law, and we're going to come back to the second law in a little bit. But the third law of thermodynamics gives us this reference point for zero absolute entropy. And that third law states that a substance that has zero absolute entropy is a perfect crystal which exists at absolute zero. So a perfectly ordered crystalline substance existing at absolute zero has an entropy of zero. There's no vibrational movement, there's no translation, there's no rotation, all motion stops, and we condense down to one very specific microstate. And this is going to have our entropy of zero. So that's our reference point for zero absolute entropy. Now, there's an important point to be made here. It turns out that we can't reach absolute zero in the lab. We can't cool anything down that cold. We can't reach negative 273.15 degrees Kelvin. It's experimentally impossible. So as a result of that, this is kind of a hypothetical case, right? This zero entropy. And then as it turns out, all substances have positive entropy, or have positive S in terms of their absolute entropy that's associated with them. Because we can't reach this reference point, all substances, regardless of what it was, their absolute entropy will be a positive number, okay? So then, why not try to predict what the entropy change might be based on what we know about entropy, and see if we can do this in a qualitative sense first, and then we'll become more quantitative in a couple minutes. Now, before we move on, we should define the change in entropy for a process. Now, again, in chemistry, whenever you think change in a variable, you see something like this, right? Triangle S. So delta S is our change in entropy. How can we compute that? Well, there's several different ways, but a simple equation is just to use our approach final minus initial. So if I could estimate what my final absolute entropy is, for a sample, and likewise, if I could compute my absolute entropy for my initial case, I could just do final minus initial, and that's my change, and that's what I want, and I'll be set, right? So let's think about this for three different processes. And what I'd like to do right now is not compute my delta S quantitatively, but just predict the sign, whether it's going to be positive or negative. The first process is water, vapor, condensing into water liquid. So what do we think about that? Well, a few minutes ago we decided that the gas phase sample, doesn't it have very high entropy or disorder? There's lots of different ways to distribute our energy in a gas, but what about in a liquid? In a liquid water, the entropy is kind of just more moderate, right? So I don't know, let's write a sideways arrow. It's not super low, right? But it's kind of in the middle. So maybe a double-sided arrow or something like that's appropriate. So if I want to do final minus initial to compute my entropy, seems like I'm going to the liquid, so the liquid is my final state. Shouldn't that have lower entropy than my gas? My gas is very high positive entropy. My liquid's lower positive entropy. So it seems like if I take a smaller number and subtract a bigger number, I'm going to get a negative answer, aren't I? I'm going to get a negative result. So sure enough, for that phase change, the condensation associated with that, our entropy is going to decrease, and the sign is going to be negative for delta S. What about the second process, though, in B? solid carbon dioxide subliming. Now, maybe you're not familiar with what that means, okay? So let's write out a chemical reaction. That process is a phase change. Carbon dioxide is a really good example of this. You've probably heard of dry ice, right? What dry ice does is it's solid carbon dioxide that basically evaporates to gas phase carbon dioxide in a single step. It doesn't pass through a liquid phase, it just evaporates. It turns out that snow and ice oftentimes does this as well. In the wintertime, it's a major removal process for snow and ice, not just melting. So that's what we're talking about here, is this specific process of solid going to a gas. So the gas is our final spot, and the solids are initial. So if we think final entropy minus initial, well, this gas, that's going to have really high entropy, isn't it? And the solid, carbon dioxide, is going to have really quite low. So if I do final entropy minus initial entropy, I'm doing a large number, a high number, minus a small. I gotta have a positive sign, don't I? Entropy is going to increase by a lot. Huge increase in entropy in this case, okay? Not even close, beginning and the end. That's a huge positive increase in entropy. And it turns out that large positive increases in entropy like that are good for spontaneity or things actually happening, okay? So just kind of give you a hint on where we're going with this. Now, we got one more example here, and letter C. Let's tackle that one. In letter C, we got a chemical process. 2 copies of N2O gas make a copy of oxygen and 2 copies of nitrogen gas. Well, this one's harder to figure out, isn't it? Because we've got a gas phase reaction that makes gases. So it's not like we're going from a gas to a liquid or a liquid to a solid or a solid to a gas or vice versa. Here we've got this reaction in which gases are everywhere, okay? So we can't just look at the phase only to predict the outcome. But what we will look at is the number of moles consumed and produced for reactants and products. So over here on the left, I've got 2 mole of N2O as written, and over on the right, I've got 3 mole of these gases as written. So I'm increasing my number of moles of gas by carrying out this reaction. And it turns out that if I do that, if I make more gas, that actually increases entropy as well. Okay, so we're going to have a delta S that's positive for part C. Okay? All right, so hopefully you're getting the hang of predicting the changes in delta S in terms of the sign. And we're actually going to get more quantitative here now in a few minutes. So we can always compute the change in entropy, delta S, as S final minus S initial, where those S terms are absolute entropies of the sample of matter that we're considering at that very specific set of conditions. If our delta S is positive, what that basically means for us is that we've increased the entropy through carrying out this process. We've increased the ability for the chemical system to distribute its energy, okay? So what types of processes will increase the entropy of our system? Well, any chemical reaction whose products are in a more randomized state will increase the entropy. So if we're taking a solid and we're making a liquid, that's good. Delta S will be positive. If we're making a gas from a liquid or a solid, that's even better. Delta S will be positive. Reactions that have a larger number of product molecules than reactants generally increase the entropy. Increases in temperature increase the entropy. And lastly, this last one's really important as it turns out. If you have a solid like an ionic compound, when you put it in water, that ionic compound frequently dissolves. These ionics compounds are frequently strong electrolytes. And remember what we said happens when that occurs is that the ions dissociate from one another. The ions break apart and they are surrounded by water molecules. That process increases S. Because the ionic compound is a highly ordered crystalline solid with repeating positive and negative charges. If you dissolve that particle of ionic compound in water, you completely mess up that. You now have the ions in water surrounded by water molecules. You've completely broken down the structure of that complex ionic compound that was highly, highly ordered to begin with. And that's important because it leads to a huge positive increase in entropy. Now, why is that crucial to us? Well, ionic compounds, if you think about their dissolution in water, you've got this ionic compound of cation and anion, which are packed, right, very, very close together. You've got these positive charges and negative charges in close proximity, don't you? Do we think energetically that system is just going to want to break apart? I mean, is this cation going to want to separate from the anion? No, probably not. It's going to cost us a huge energy price to pay to separate those particles. However, remember I said a few minutes ago that increasing the entropy is going to be good? If I dissolve this stuff in water, it's going to be a huge energy price to pay to separate these ions apart. But the system's going to be a lot more disordered if I do. And that's going to help dissolve my ionic compound. And that's actually kind of one of the reasons why they tend to dissolve. We'll get back to that stuff later, okay? Now, how can we quantify entropy changes during a chemical reaction? There's a couple different ways that we're going to have to do this, a couple different options in our toolbox. One of them, as it turns out, will be this equation. And we're actually going to use this equation later in a subsequent lecture, not this lecture, but a subsequent one. And it basically tells us that the entropy change that's going to be associated with our system or chemical reaction can be estimated by Q, the heat flow for a reversible process, divided by T, the Kelvin temperature at which that process occurs. We're going to come back to this equation in a subsequent lecture to do a derivation of a different equation. We're not going to do that right now, and it turns out we're not going to use this equation all that much. I guess you might see it in an online homework problem or something like that, okay? Or you have to take Q and divide it by the Kelvin temperature. But other than that, I don't anticipate using this equation all that much, other than this derivation. But nonetheless, that's one way we can compute the entropy change for a reaction. But turns out there's going to be another way. This, I think, is a lot more powerful for us, okay? And I'm going to call this the bookkeeping approach. The bookkeeping approach. We can quantify changes in entropy for a chemical reaction by this bookkeeping approach. And the reason why this works is because we are able to consider each individual reactant and think about the entropy that each substance, each reactant and product contains. And that's a weird thought, okay? But remember earlier we said that entropy is an extrinsic property of a material, okay? There's different abilities of different materials to distribute energy within them, whether that be by vibrations, rotations, translations, what have you, okay? And that's a function of the material itself and the temperature at which it's held at. So if I specify very precisely what material I'm talking about, its very specific phase or organization, it's allotrope, it's organization, and I also specify very precisely what temperature I hold that material at, I can start thinking of the situation in this way. It's almost like a particular type of material at a very specific set of conditions contains a certain amount of this entropy that we're talking about, okay? And because of that, I can take a bookkeeping approach to track the change in this variable entropy over the course of any reaction. And it's actually going to be pretty simple to do that, okay? So entropy, or absolute entropy, that's contained within a material scales with the amount of material present, okay? And for our purposes, what that's going to mean is that we're going to define entropy that's contained within a material on a per mole basis. That's going to be important. We'll find that entropy also varies with molecular complexity or molecular weight and the temperature that we need to hold this material at, okay? And lastly, we know our 0 point is set by the third law of thermodynamics. That says that zero entropy is only for a perfect crystal at absolute zero. Now, we can't experimentally get there, but that's our reference point for zero entropy. And because of that, everything else has a positive standard molar entropy. And again, this business of positive molar standard entropy, notice I specify it per mole. It's the entropy per mole of material under a standard, very specific set of conditions. So if we think about entropy in these terms, all we need to do then is to discuss what are these very specific standard set of conditions. These are known as standard conditions. Okay? Everything is important. Every detail matters when you're starting to talk about entropy contained within a sample of matter. How much of it matters? Do you have half a mole, 1 mole? Okay, that matters. So when we do these computations, we usually specify things on a per mole basis. And that quantifies how much material we've got. More material, more microstates, more entropy. Another concern is temperature. So we have to specify temperature. We do so at 25 degrees for our standard set of conditions, our standard state, as we like to call it, okay? Now, what if we're dealing with a gas? Well, we might want to specify a partial pressure or a concentration of the material. So for a gas, the reference state is 1 bar of partial pressure, which is very close to an atmosphere. What about if we're talking about an aqueous ion? We need a standard reference state. What is it going to be? Well, for aqueous ions, 1 molar concentration of that ion in aqueous solution is our standard reference state, our standard state. Okay? So 1 molar concentration of our ion, 1 bar partial pressure of gas, 25 degrees Celsius, about 298 Kelvin, is our reference temperature. Now, why is all this important again? Because we're defining a very specific set of conditions that if we achieve, we can define standard molar entropy values for all materials. All right, this is super cool, all right? So if we define a reference temperature and a reference state, and again, our temperature is at 298, and our reference state is 1 molar for aqueous ions, their concentration should be 1 molar for anything in the aqueous phase, and 1 bar partial pressure for gases. If we meet those conditions, that standard state, on a per mole basis, we can define a standard entropy of that material. Now S is entropy. If I have this little 0 behind it here, that tells me I'm operating at the standard set of conditions. That's what that means. So when you see this S0, it's read as standard molar absolute entropy. And what that is it's a number that basically tells me, essentially, you can think of it this way, right? How much entropy a particular chemical or material has under a very specified set of conditions. And I keep coming back to that, but it's really important. It's got to be at this temperature. If it's an aqueous ion, it's got to be 1 molar concentration. If it's a gas, a 1 bar partial pressure. You've got to specify whether it's a solid, a liquid, a gas. You've got to specify exactly what the chemical is to use this concept. You've got to specify if it's a solid of carbon and it has more, or a solid like carbon and it has multiple allotropes. You have to specify very specifically which allotrope. Is it diamond? Is it graphitic carbon? What type of ice it is. All these details are extremely important, but if you're able to do that, you can quantify the standard absolute entropy, which is contained within that very specific material. Now, where do you find these magic values at, okay? Well, it turns out that values for standard molar entropies can be found in appendices of chemistry textbooks. You're going to find one in an appendix at the end of your textbooks. They can be found online. I'm pretty sure that your homework solution to Connect, where you have to work these problems for grades, they are going to give you a table of standard molar entropies, or else it will be given in a table, okay? Or given in the problem. You can find these in reference data. Now, the values for standard molar entropy are typically joules per mole of the substance in question. So you see how it's specified on a per mole basis is an extensive property. But it's entropy per mole, basically. We can think about it that way. So what I'm saying is that you can look up these standard molar entropies in these tables and then use them in this bookkeeping approach that I'm about to tell you about, okay? Now, what do these tables look like? This is one that you might find in a textbook, okay? You'll find something like this probably in your textbook in chapter 20. Unfortunately, I've got a table from a different textbook that thinks this is chapter 17, but it's chapter 20 in your textbook, so you'll have to find a table in chapter 20. But what does this table look like if you were to look at it? Well, if you review the table itself, you'll see that there is an S0 term. That's our standard molar entropy value in joule per mole per Kelvin. And if you look, there are values that correspond to lots of different substances. And this is only a partial list. There are hundreds of values in the appendix in your book for many different substances. But you'll see that each chemical is assigned an S0 value on a per mole basis. We've got gases in the first column, got liquids here in the second column, got solids here in the third column. And again, what do you tend to notice if you're comparing any one particular substance? I guess we can compare liquid and gas phase water here and here. Which has the higher entropy? Oh, it's the gas, doesn't it? Much higher entropy. Now, if you're comparing solids with liquids, don't solids tend to have lower entropies than the liquids and the gases? So we made these conclusions, these qualitative conclusions that we made earlier, really extend here, okay? These are just the specific values of standard molar entropies that are associated with each of these chemicals. So what are some other trends that we see in terms of standard molar entropy? Let's talk about trends in the data. Effective phase is the first trend that I want you to talk about. Actually, I just referred to this. The gas state has larger entropies than the liquid state, and the liquid state has larger entropies than solids. And again, the example that I just gave you is for water, comparing liquid and gas phase water values from that table. For standard molar entropies, or S0, we can see that the gas phase has a much higher standard molar entropy. And this will always be the case. If you're comparing identical substances, gas has higher entropy than liquid, liquid has higher entropy than solid. Another trend that's apparent in the data, this is a general trend, okay, has to do with the effective molar mass. How does the molar mass of compounds affect the entropy? It turns out the larger the molar mass, the higher the S0, the higher the entropy. And this can be seen if we consider the trend in our noble gases, which is in this figure. As we go from helium down to xenon, our S0 value increases. Helium's the smallest, xenon's the largest, down at the bottom. We also know that the atomic size or radius increases as we move down from top to bottom. Helium's a very small atom, as is xenon. Or xenon's a very big atom, okay? Now, what is the trend in molecular weight between these? Well, xenon's way at the bottom of our periodic table. It's very heavy and big, right? Our helium's at the top of the periodic table. It's very light. And the general trend reflected as we go from light atoms to heavy, the S0 increases. Okay, so the larger the molar mass, the larger the standard molar entropy. And the reason why this is it's thought of that in the bigger atoms that have more electrons, the allowable energy states are much closer spaced together, and this allows for better distribution of the energy throughout the system on a per atom basis. I mentioned earlier these substances, graphitic carbon and diamond. Okay, graphitic carbon and diamond, two allotropes of carbon. It turns out that both graphite, what's in your pencil lead, and diamond are both carbon. They're both made of carbon. They're just arranged in slightly different ways. Okay. They're both solid carbon, but what's different between carbon atoms in diamond and graphite is how they link to one another, or essentially bond to one another in the solid. We'll start with graphite, which is shown on the bottom. Graphite is famous for having sheets of carbon atoms. Each carbon atom is connected to three others in graphite, okay? And they form these planar sheets that basically stack on top of one another. And that's really good for pencil lead, because when you take a piece of pencil and write on a piece of paper, what basically happens is these sheets just get torn off of the crystal of graphitic carbon, and they leave their mark behind, okay? And it's easy to tear these sheets off because there's not really anything holding them together. Very weak dispersion forces hold the sheets together, and that's all. But in this case up here of diamond, we have a very different arrangement of carbon atoms. Now the carbon atoms are bonded to one another in a tetrahedral arrangement, which is three-dimensional. And notice that there are these bonds that link carbon atoms together up and down in the structure. We're linking the carbon atoms together not only in 2 dimensions, but in 3 dimensions. In graphite, the carbon atoms are only connected in 2 dimensions. But in diamond, the atoms are connected in 3D. So because of that, diamond is a very hard material, isn't it? Because to get that to scratch or to deform, we've got to start breaking a lot of covalent bonds between these carbon atoms, which are strong. But in the graphite, the sheets were just connected by very, very weak dispersion forces, right? So we can break these sheets off easy, but in diamond, not so much, okay? So anyway, back to the original topic. What about standard molar entropies of these two materials? If you compare the standard molar entropies of the two materials, you'll find that the S0 values for diamond is 2.4, for graphite it's 5.7. You see the value for graphite is much higher, isn't it, than for diamond. We probably would expect that by this discussion that we had of the graphites just having these sheets and the diamond being, carbon atoms and diamond being really locked in place, okay? So of course the graphitic carbon is much less constrained. It's going to have the higher entropy. But another thing that I want you to take from this is that the specifics here are going to be so important when we start working problems. You've got to specify not only that you've got carbon in the solid phase, but you have to specify what specific allotrope of carbon you're dealing with, because they're not the same. They have different standard molar entropies, don't they, okay? So you're going to hit the specifics and the details of the chemicals that you're working with, both for reactions and products, are going to be super, super important in the remainder of our discussion here for this chapter, okay? All right, another trend. What about, I'll call here molecular complexity, molecular complexity. What do I mean by that? Well, I'm basically talking about the size of the molecules in terms of how many atoms they have bonded together. It turns out that more complex molecules that have more bonds generally are going to have larger entropy. So the more things bonded together have larger entropy. And the reason why that is because the more bonds that you add to a molecule, the more vibrational modes that that molecule can exhibit. There's more places to distribute the energy in that chemical system, and that means it's going to have a higher entropy. So to compare and contrast, let's consider argon and NO. Both of these are gases at room temperature. They have reasonably similar molar masses. However, if we look at the standard molar entropy, the value for NO is a little over 210, but the value for argon gas with no bonds is about 155. The value for NO, where a bond exists between the nitrogen and the oxygen, is higher, isn't it? And that's because once you start adding bonds, you start adding these vibrational modes and energy can be stored there. That's going to increase the entropy, right? So more bonds, more energy states available, allowing more dispersal throughout these states. I mentioned a few minutes ago dissolving ionic compounds. This is important a topic as well as it relates to entropy, because solids have relatively low entropy. The reason why is because the particles in a solid are really locked in place. They don't have translational freedom of movement. They don't have a lot of rotational freedom of movement. At least they're inhibited in that sense. So they're a low entropy state. But when we make an aqueous solution of something, the entropy can go way up. And we see that here in this example for this potassium salt. The solid has a much lower entropy than does the aqueous solution of the same substance. Now remember, aqueous solutions where we take that and we dissolve it in water. So here we're specifying a mole per liter of that material in water because that's our standard reference state for an aqueous solution. But our dissolved solid has a greater entropy. And the reason for that is because we've taken these particles, we've dispersed them throughout the liquid solvent. Now they're more free to move, to translate, to rotate, to vibrate. That's going to increase the entropy of that system. All right, so we're moving towards the last topic of this video now. What I want to get back to is, and this is one of the more, there's a lot of stuff that's important in the video, but this is one that's important for problem solving, okay? We're going to get back to computing the change in entropy for a reaction using our bookkeeping approach. We now have a useful metric to allow us to quantify this entropy that's contained within a given substance. We call that the S0, or our standard molar entropy. So on a per mole basis, it's for a very specific set of conditions, 298 Kelvin, 1 molar concentration of an ion, or something that's dissolved in aqueous solution, 1 bar partial pressure. But if we specify those very specific conditions, we can quantify this entropy contained within the material, if you want to think about it that way. So now we're going to get into that bookkeeping approach that I mentioned earlier. And that bookkeeping approach is going to look at the entropy of our products and the entropy of our reactants and compare them. And guess what? That's going to allow us to compute the entropy change of our reaction. So the standard entropy change of a chemical reaction can be found using this equation. It is nothing more than the difference in entropy between the reactants and the products. A very similar equation was used in General Chemistry 1 to compute the enthalpy change associated with reactions. So let's take a look at what all the terms are in this particular equation, so that we can understand it better. So this first term deals with the products. It's products minus reactants, basically. And we're told to sum or add N times S0 for our products. What N is the stoichiometric coefficient for a particular chemical within a balanced chemical equation. And our S0 is the standard molar entropy for that material that we would look up in a table. You simply take the standard molar entropy and multiply it by how many copies of it are governed in the stoichiometry of the balanced chemical equation. And you do that multiplication for each and every product of the reaction. And then you simply add the results together. And you do the exact same process for the reactants. You find the standard molar entropy for each reactant. You find the stoichiometric coefficient for each reactant. And you multiply them together. You add them up. Products minus reactants is our change in entropy for the reaction. Now, the standard enthalpy for formation, delta H for a particular substance, or for an element was 0 back in General Chemistry 1. However, the point that I really want to get to is that the absolute entropy of anything has to be a positive number, okay? There are a few exceptions to that, as it turns out, which maybe you'll find in one of these data tables. They're for aqueous ions. But generally speaking, the absolute entropy of just about all substances is going to be a positive number, okay? So what I'd like to do now is look at a sample problem using this concept, because this type of calculation is pretty important for this chapter. They're posed like this. Calculate delta S0 reaction. That's what? The standard molar entropy change for a reaction. And you're given the reaction. This is it. 4 copies of ammonia, add to 5 copies of oxygen to make 4 copies of NO and 6 copies of H2O. Now, if you're not, and you actually just asked for the delta S0 here, okay? Now, if you're not given the standard molar entropies, the S0 terms for each of the compounds, your first step is always to find that information. Now, my guess is sometimes you're given that in the problem, but if you're not, you can use the appendix of your textbook. Now here, we have this very useful data table. And within this data table, we are given S0 values for ammonia, oxygen, NO, and H2O. These are the values that we'd find in that appendix, okay, for each substance. Notice that each substance is given their own value. That's the own internal entropy of that material. Notice that it's also specified on a per mole basis. Another thing that I want you to look at here that might be easy to miss, but it's a place where people make a lot of mistakes. Look at the states of matter, especially if you're using that appendix in the back of your book. You really need to be careful about this. Look at the states of matter. These are all gases, and that's what we have in this problem, okay? Which is good, because that's what we want. However, it's really easy to go to one of those appendices in your textbook and pick out the value like for H2O solid or H2O liquid. And that's a different number. And if you use that number in this calculation, you'd get the wrong answer, okay? You need to use the value for the gas because that's what's specified in the problem. That's what's specified in the chemical equation for this reaction, okay? So I really want you to keep that in mind. Pay particular attention to the states of matter, very, very specifics that are associated with that. Because it's very easy to pick the wrong S0 value from the back of your book if you don't do that. Just from experience, I know that that's a very, very easy mistake to make. But once you look up those numbers, we start to be a little bit closer to a solution. Because our summation rule for computing the entropy change associated with the reaction tells us to sum the terms for the products and subtract the sum of the terms for the reactants. So how can we achieve that? Well, as I mentioned earlier, we're going to have to add up terms for our products. That's the water and the NO in our reaction. So notice that what we do is we take a 4, which is going to be our N value, for NO, and we multiply it by the S0 from our table for NO, which is 210.8. Stoichiometric coefficient, 4, times the value from the table. Now we have to add that to our term for water. Each product gets its own term. Now in the balanced chemical equation, 6 copies of water were involved. So I multiply 6 times the S0 value for water. If I look on my table, that's 188. 6 times 188 is what I need to add to my equation. So I add that together, that result, because that's my product's term. Water was a product, my NO was a product. I do 4 times that number, 6 times that number, add it together. I've successfully completed that part of the equation. Now I do exactly the same thing for my reactants. I see that 4 copies of ammonia are involved in this reaction. So I take a 4 and I multiply it by my S0 term for my NH3, my 192.8. I notice that 5 copies of oxygen are involved in this reaction. So I take my 5 and I multiply it by my S0 term for my oxygen, my 205.2. I take that, 5 times 205.2, I add it to 4 times 192.8, and I have successfully completed my reactants term. I just find the difference between these now. I do products minus reactants, and I find my delta S0 reaction is 178.8 positive joule per Kelvin. So using the summation approach, we can compute this standard entropy change for any reaction that we want to. That's going to actually be a super powerful thing to do. Just like we can compute delta H0 for any reaction we want to by a similar summation approach. We can now compute the standard entropy change associated with any reaction we want to. Here we did it for this ammonia with oxygen, making some NO and 6 copies of H2O. We might expect that there'd be a slight increase or positive sign on our entropy, because it looks like to me we're making 10 moles of gas as a product and we started with 9. So we're making more moles of gas. It makes sense there's a positive change, right? And that's in fact what we got when we did the calculation. But what's important about this is that this approach can always be used to compute the standard entropy change for any reaction that we wish to consider. And that's a super, super powerful thing, okay? All right, so this was my first video here using the screen grab of my iPad. So hopefully I'll get a little bit better at using my pen and so on and so forth. I'll keep looking at multiple different options, but the usual studio that I use to record videos is pretty booked up at this point. But I think it worked out all right, and you can always go back and look at this again if you have more questions. And definitely feel free to email or Skype if you have any further questions. The next video is going to be using this concept of entropy for a chemical reaction and combining it with enthalpy, the delta H of reaction, to produce an equation that allows us to predict whether or not a reaction will occur. And that's kind of the exciting point of this chapter 20. All right, so we'll see you